All right, can you see my screen?
Yes, yes. Okay, so I think you can start.
All right, awesome. Hello, everybody. My name is Konstantin, for those that don't know me, and I'm super excited to present to you all the paper that I've submitted, or that's on arXiv on planetesimal formation and streaming instability. And this is work that I've done with my collaborators, Ruth Clay at UC Santa Cruz and Hubert Klahr at the MPIA for astronomy, and also Hans Baehr, who is now a postdoc in Las Vegas. And before I start, I also want to thank the organizers of this conferences. I can only imagine how much more work it must have been to organize such a conference without actually having a venue. Right, and I also want to say that my internet connection has been disappointingly inconsistent over the last couple of weeks. So if the stream goes unstable, I apologize. All right, with that out of the way, I'm going to talk about planetesimal formation and streaming instability, and also Kelvin-Helmholtz instability. And I want to put the focus really on this planetesimal formation aspect. And I think this is maybe in contrast to excellent talks we heard yesterday, where the streaming instability was sort of in the foreground, and then they talked about the implications for planetesimal formation. And I want to go the reverse order. And after a quick recap to make sure that we're all on the same page, I want to talk about how we in this paper view planetesimal formation in the gravitational collapse scenario, and then afterwards talk about the implications for streaming and Kelvin-Helmholtz instability. All right, so let's just start with a quick overview of everything that's going on. So I drew this brief schematic of a disk. You all know this. We have a gas disk, and in the midplane, there's this dusty midplane. The entire disk is subject to a pressure gradient, which only acts on the gas, which leads to a difference in orbital velocity. And this difference then leads to radial drift of particles and orbital decay. And this drift is the fastest at meter-sized particles, so Stokes number 1 particles. And this sort of very rough overview of the meter-sized problem is maybe one of the most challenging aspects of planetesimal formation, because you need to form planetesimals fast. And yeah, so as you know, there's multiple scenarios on how to overcome these growth barriers. And the first one that I want to mention is the Goldreich-Ward mechanism here. And a very thin, the entire thin midplane of the entire thin particle midplane fragments and is subject to gravitational instability. And for that to happen, you need a particle scale height that's about 10 to the minus 4 times the gas scale height. And this is actually hardly possible, because the Kelvin-Helmholtz instability stirs up particles to heights about 1 or 2 orders of magnitudes higher than that. And this Kelvin-Helmholtz instability always occurs, because as soon as if you have a particle layer that's embedded in a larger gas disk, then you will have a vertical shear and azimuthal orbital velocity. And this, in addition to buoyancy oscillation, will trigger Kelvin-Helmholtz instability if the gradient in dust-to-gas ratio is steep enough, and also the gradient in vertical shear. All right, we've also talked a lot about particle traps that may stop drift, and these may be found in planet-induced gaps, which act as pressure bumps. But I'm going to try to stay a bit more general and talk in general about the direct gravitational collapse of a local particle overdensity, and that may occur within a trap or in a pressure bump, but also just not. And in that context, often mentioned is the streaming instability, which has been explained excellently yesterday by Jonathan Squire and also Chao-Ching Yang and others. So I'm just gonna, again, recap the couple of ingredients that we need. We need this pressure gradient, and then we need particles that are coupled to the gas with a feedback term also included, and also a local dust-to-gas ratio of unity, and sort of marginally coupled particles tend to be better than smaller particles. All right, before I present our sort of simple picture with our schematic, I would just want to go over the sort of the key symbols that I'm using here. So for the pressure gradient, I'm going to be using beta. You can think of this as just the aspect ratio if the power law exponent of the density is just order unity. And the Stokes number, which quantifies how well the particle is coupled to the gas. The particle concentration or metallicity, I just want to note that this is the height integrated dust to gas ratio. So this is not going to be unity. And then also maybe a bit more surprising in the context of Turing instability, I want to introduce the Numerical parameter, which quantifies whether or not a gas region in the disk is subject to gravitational instability. So if Q falls below unity, so if, for example, if the temperature decreases or the gas density increases, then the gas disk will fragment. And if Q is larger than unity, it will be stable. All right, so let's just, I made a small sort of schematic of cloud collapse, and we'll just start by envisioning a particle cloud that's embedded in a turbulent gas medium. And if it has mass, then it wants to collapse under its own self-gravity. But if there's turbulence, turbulent may be strong enough to actually prevent that collapse, and the cloud won't form a planetesimal. And this can be expressed by some length scale, which I'm just calling L diffusion here. So if this is the case, then turbulent diffusion will prevent collapse. So let's just make our cloud bigger, such that the self-gravity, such that turbulent diffusion won't prevent collapse anymore. Well, if it's too big, then tidal gravity may prevent collapse, and the cloud will be ripped apart before it can form a planetesimal. And this is likewise attached to a length scale, which I'm calling L Hill for the Hill density, which just quantifies whether or not a cloud is ripped apart by stellar tidal gravity. Right, so in summary, the cloud can only collapse if its size lies in between those two length scales. Only then self-gravity wins. And I think this is sort of the foundation of how we view gravitational collapse here, that self-gravity must overcome both turbulent diffusion and tidal disruption. And this is very similar to the Tumre consideration, where the gas self-gravity must overcome gas pressure and tidal disruption. So it's just sort of a modification of that. And this is also why I introduced the Numerical parameter earlier. I just we wanted to formulate the criterion in a very similar fashion, so it's easier recognizable. All right, so if you plug in the symbols and do the math, you'll find the diffusion length scale by comparing diffusion time scale and contraction time scale, and this is arises just from comparing tidal gravity with self-gravity. And then if you just do some algebra, you'll arrive at this criterion, which has a 1 here, very similar to the 2-mode criterion. And yeah, I just want to highlight the proportionalities. So if Q increases, so if the disk mass decreases, then it's easier. If the disk mass increases, it's easier to collapse. If the metallicity increases, it's easier to collapse. And if the diffusion coefficient, which is delta, if that increases, so if you have a more turbulent disk, then it's harder to collapse. All right, so this is nice, but I also wanted to test it. Oh, I first want to mention that in the marginally unstable scale, so if the right-hand side of this equation is equal unity, then we can actually recover the critical length scale from Hubert's and Andy's paper that is submitted. It was also published a couple of years ago, which is super nice. And that length scale actually corresponds to the size of the marginally unstable particle cloud in that picture. And it's also, if you do the instability analysis, it's the most unstable wavelength. All right, with that out of the way, how can we test this criterion? Well, whilst the Stokes number and Q are, at least in simulation, input parameters, the diffusion and Z, and so the particle concentration, are regulated by local hydro instabilities in the particle layer. And this was also pointed out nicely by Chao-Chin yesterday, that the streaming instability itself, and likewise the Kelvin-Helmholtz instability, do generate turbulence itself. They're not just only concentrating particles, they also generate turbulence on small scales. And this is super important for setting this lower limit. So it's really a double-edged sword, both Kelvin-Helmholtz instability and streaming instability in that sense. Right, so for that reason, I conducted numerical simulations, 3 numerical simulations with the pencil code, which solves
5 minutes left.
All right, which solves the hydro equations for gas with Lagrangian superparticles. And I did this in the Turing box frame, which I sort of visualized here. We saw that yesterday also. And the next slide, I'm going to show a movie. So on the right-hand side, you'll see sort of the top-down view. On the left side, you'll see a cross-section. So here you will see the apparent motion due to Keplerian shear. And on the left side, it's just particle settling. All right, so this movie should start. There we go. So you also particle settling, and they get sort of blown up to a scale that's characteristic to Kelvin-Helmholtz instability. And here you're already in the nonlinear saturation phase of streaming instability. And while this is running, I'm just going to go over the approach we chose to test the criterion. So after we are in this nonlinear saturation phase, so at the end of that, we let it evolve until we are in this phase, and then we measure this turbulent diffusion, so delta, and also the local particle concentration. And then we turn on self-gravity with different values of Q, and then check if planetesimals form. All right, so I'm just going to fast forward. This is the final snapshot. You can nicely see the axisymmetric structure of streaming instability. And this is the same snapshot, just twice, so don't get confused. This is both the radial azimuthal plane. And here is a low mass scenario, and this is a high mass scenario. And if you turn on self-gravity, you can see that this disk basically is qualitatively unchanged, whereas here we clearly collapsed and formed planetesimals. We can quantify this a bit better by solving our criterion for Q. Then we get some critical Q value that must be surpassed, must be that Q must fall below for gravitational collapse to occur. And we tested this and it worked quite well. Here we have some minor inconsistency. This yellow line should have collapsed also if we believe our analytical criterion, but I think this can be assigned to some resolution issues and also maybe just our measurement of delta may be a bit inaccurate. Yeah, so what are the implications for Kelvin-Helmholtz instability and streaming instability? And this is the part that's also in my paper that I'm just glossing over for brevity in this talk. Both instabilities actually set the scale of the particle layer and thus the diffusivity in the absence of additional external turbulence. So this is something we noticed, that the height of the particle layer and the radial width are sort of set by the same length scale. And we know this height from the Richardson criterion in the Kelvin-Helmholtz instability. And then if this is actually the process that's determining that's dominating the diffusion, then you can actually replace delta over Stokes by a very simple expression, and only the pressure gradient appears in this equation. And the other part is that I think in the framework of our criterion, streaming instability and also the Kelvin-Helmholtz instability are a bit disentangled from planetesimal formation. Let me show you what I mean by this. So here, this is a set of simulation. The left panel shows the situation or the snapshot right before self-gravity is turned on. So in these two cases, we kind of have streaming instability clumping. This is a higher resolution than this one. And here, the metallicity was chosen such that we don't get strong streaming instability particle concentration. And all these right panels are just the situation after self-gravity was turned on for different values of Q. And I just want to highlight those two panels. So in this one, we clearly have streaming instability clumping before self-gravity is turned on. But then we turn self-gravity on and we still don't form planetesimals. This is because Q was just chosen super high or a very low mass disk. And likewise, if we have a no streaming instability clumping, we can just decrease Q a lot, for example here, and still form planetesimals, even though we don't have prior streaming instability clumping. Yeah, and I think this is super interesting. This brings me to my summary. So the first point is the one that I didn't really go into a lot of detail here, but that Kelvin-Helmholtz instability and streaming instability regulate diffusion on the scales of planetesimal formation. assuming they are the dominant processes that act on that particular particle layer. I think this is the case if there's, for example, if VSI is not really dominant and if there's no MRI. And then the second part, in this criterion, gravitational collapse can be assessed by only considering the Q value, the particle concentration, the diffusivity over Stokes number. And then lastly, the fact that streaming instability and planetesimal formation, I don't think they are equivalent, so to say. So you can think of, like I was able to set up simulation where I have strong streaming instability clumping and cannot collapse. And likewise, I've essentially no streaming instability clumping and can still collapse. It just, like, Q matters also is basically what I want to say. All right, and with that said, I think if you're interested, you can check out my paper. It's on arXiv, and especially for those of you that do similar simulation of planetesimal formation, I'd be super interested in learning how my criterion or how our criterion applies to your simulations. Yeah, and you can also email me, of course. Yeah, and I'm happy to answer any questions.